Good morning, everybody. We're going to talk about debugging stand programs. It's yeah, we'll get into it. Here's sort of what we're going to cover. We're going to recognize some of the common stand pathologies. We're going to try to diagnose non-identifiable parameters and figure out what to do with them. Different strategies for it. We'll fix divergences and runtime issues, and then we'll through this whole process we'll just like we'll go through how to debug programs, and you'll see the different sorts of resources we have for debugging and making things faster. um for today, please ask questions. I'm pretty good at debugging Stan. I'm actually really good at breaking it. Like, I can make Stan do bad things really easily. um I've been working on Stan since the very beginning, so what's second nature to me might not be second nature to you. What's really easy, what I've been staring at for many years, might be new. So please speak up. And if you've seen it a bunch of times, um, we can skip over it and go on to something else. Um, and if we're at the end of this and we're all bored, I can switch over to talks or other talks, or you know, talk about different stories about how Stan was built and whatnot. All right. Has everyone tried clicking on that link that Phil sent out? Has anyone is anyone able to get there? If you are, it looks like this. It has all the materials inside there.
So I do think they're in. Quite a few people are joining, Daniel. So just
Okay.
try to use the link that I shared. I think the link that you
Yep.
shared might take you to the workshop, your environment. I think we want to take them to their own duplicate space, which will
Yep.
be that
I
second.
just deleted it.
Oh, okay.
Great.
Perfect.
Yeah,
Great.
that's better. Yep.
Yep.
You got it?
I got it.
Oh my God. Cool. Okay. All right. Um, so debugging 101. What does it mean to debug something? By the way, like, seriously, if you have questions, please ask. Please ask in the chat. You can jump on if you're allowed. Please unmute yourself and ask questions. I don't like talking in a vacuum. It's kind of weird talking to a bunch of people in a vacuum. So, please do. But yeah,
I-
debugging 101. Yep.
I'm always here, Daniel, if you need to
All right.
chat.
Thanks, Phil.
Yeah.
Uh, Debugging 101. I mean, the first thing you have to understand is that you have a bug, right? So you have something that's not going right. You want to reproduce the bug. You want to put inputs in. Um, the output is messed up. So something between the input going in and the output, there's something wrong. The next thing you usually do is you simplify the code until you find out where it breaks. So you're trapping where the error is. You want to inspect the state during that process. So figure out where along the process something is not what you expect. You're going to check your assumptions. Maybe something that you thought was going to happen didn't happen, and then you'll fix it and test it and just re restart the process over and over again. What makes debugging in Stan hard? So we're talking about Stan. Um, One of the issues is that the Stan program output is stochastic, meaning in normal software development, you put an input, you run your code, you get output out. Um, Nothing changes. It should be exactly the same. There is a caveat. Sometimes you run into hardware issues or race conditions where you run the same code and it does change run to run, but for the most part, it shouldn't. Um, but any stochastic program that you're trying to debug, you put input in, you run with a different seed, something else happens, and then the output isn't exactly the same. So that's one of the things that makes debugging difficult. The second thing is that, bug here is sort of a vibe. It's a feel. Your R hat isn't great. The parameter inferences don't feel right. These aren't like necessarily like you put input in and you know that the output is wrong. It's more like you feel like something isn't right. Um, Another thing that makes it difficult is reproducing bugs in stand sometimes is really difficult. You might see something fail on one chain out of 10, one chain out of 100. And if you happen to be running it that time, it fails. It might be dependent on the data. So if you take a different subset of the data that you're looking at, it might be different. Um, it could depend on the starting location. So that's also seed dependent. The other thing that's really tough is that the tools for inspecting state is actually not easy, not great. Uh, so we'll use print statements. We'll get familiar with how blocks work in Stan. And then something that's kind of really hard to inspect are the gradients in the autodiff stack. So these matter for us, but they're hard to look at. Um, Ruba, yes, the sh slides will be shared. They're actually here, and they should also be loaded in the assignment itself. So will oh no, is the workspace empty? Um,
Uh,
it's not supposed to be empty.
Let me
Let's
take a
see.
look at it here real quick.
Yeah, we'll get that set up. It'll be worth the time to fix that. Um,
Yeah, I'll take a quick look here.
sure. For any of the other attendees, if you want to use RStudio Cloud, I think it's called Posit Cloud now. Um, Click on the link that uh, Phil posted, and let's see, I should be able to paste it here. And you'll get into a space. What'll happen is it'll give you a space with RStudio. It should have these files: 1, 2, 3, 4, 5, 6, 7 files. Um, the slides is PDF, and then 5 different examples and a script to run it. Says no content.
Yeah,
Okay.
I'm gonna jump in there real quick and just see if I can figure out why there's no content. So just give me 2 seconds. I think it's gonna kick you
Yep.
out. Yeah, so no big
Yep.
deal. Okay.
All right. Let me close out for a second. Yeah.
Yeah, I think.
How can we detect content changing bottlenecks when doing multi-threading? Um, Trin, could you get add a little more detail to that question? Happy to answer it.
All right. So, Daniel, while they're doing that, I think you should be good to go now. I think it was set to private, so I changed it to open for the members. So if people click on the link that I just put in the chat box, it should now have content. If they don't have content, um, they may just have to delete the one that they clicked on before and just click on a new one, and it should open it up with all of the slides and files. So I think it should be good to go now. If anybody, yep. So people are starting to say they can see it. So I think we're good. So
Yeah,
there you go.
great. Awesome. Hey, Marcus. All right. Looks like people are getting in. That's great.
So I think if you go back and do your master one, it should be good to go. Yeah.
Oh, I clicked on the wrong one. Sorry
That's
about that.
okay. Yeah, there you go.
This one
There you
should
go.
be mine.
All right.
All right. All right, we'll get started. Trin, when you have a minute, please add more details and we'll try to answer that question. All right. I've got this um, script.r file. You don't have to use it if you don't want. We're just going to go through a bunch of examples and we're going to figure out different things. If you have this loaded, you should have command stand R loaded, dplyr, base plot, ggplot, and then I'm setting a color scheme. The first thing we're going to do is we're going to learn how to look at some state and understand output when things fail. We'll identify the issues and we'll debug by print. We cool with that? I hope. So if you run this first example, we can actually look at it. Example 1.stand. This is what it looks like. Everyone see that? Are you? I'm sure it's a bit of a pain flipping back and forth between my screen and what you're looking at. But if you take a look at example 01.stand, it's a 13-line program. There's a block ahead. These are blocks: transform data, parameters, and model. All right, Trin. We'll get to your question after this example. All right. Um, Everyone with me? If you run this line, you are missing the index for Y. Yeah, that's not the only thing missing though. So let's start. So this step here, if you're not familiar with command stand R, this step here will compile the stand program. So it's taking this .stand program, it's actually generating a C++ file. It's a C++ header to be specific. The header is getting compiled to a static object, and then that object is going to be compiled into, and we'll see an example _01 with no extension, and that's an executable. Oh, Marcus, let's see if we see same problem. Does anyone else see Marcus's problem? The command stand path has not been set yet. Oh, okay. Um, that means that the content got over, but not the settings. All right, so um, for anyone with that set command path not set, actually, let's try this. Can you type this and see if you get what I see here? Does anyone see command stand 2.3.0 to 2.37.0? Okay. So if that's what's happening, then we have to install command stand. So this will take a few minutes. Um, so please type this into I'll run it with you so I know. Oh no, mine's already done. Okay. Oh, I'm gonna run it with you so I know roughly how long it takes, and I'll answer Trin's question while we're waiting for this. So, Trin, I have a large hierarchical model and use threading across several cores with different grain sizes. However, the child process sometimes only use 75% of CPU. Some people say I should change the grain size as changing context in parallelization is extremely expensive. I did change to bigger grain sizes and models running faster with child process using 80% of CPU cores. However, I'm not sure how to tweak this grain size for efficiency. Um, the the long story is the short story is going to be that you're going to have to just experiment with it. Yeah, the shuttling data across, let's see, you're using threading. Okay. So if you're using threading, we use a shared memory system. So actually that's not true. We copy the autodiff stack at when we start threading. Something you might want to experiment with is to move your threaded process earlier up in the stack. So if you actually move it up in the code block so that it's as early as possible so that there's less things on the autodiff stack, it should copy the autodiff stack less going back and forth. There are a few other things that aren't mentioned here, like how many threads you're asking Stan to take up. So if it's only using 80% of the CPU cores, that might be some of the issue. The other issue here is um, the way threading works in Stan is that in a single log prob evaluation, it's actually multi-threading. It's not threading at a granular level. So it's trying to split the computation of the log prob across. And if that computation is really fast, there's you're gonna eat a lot of overhead. It's gonna, the time's gonna go into overhead. Um, so yeah, that's gonna be it. I mean, it makes sense that you want the grain size to be roughly split for the number of cores you have. So if you happen to know that you have 10 cores and 1,000 data points, you want the grain size to be roughly 100 so that each of them has 100. Um, but other than that, there's a lot of experimentation. Hopefully that helps. Okay, great. So people are command stand should have run by now. You can run that. All right. So the first thing, if we do this, do you see an error? All right. Um, Anyone want to tell me where this error is? What line it's on? And what the error actually means? All right. So the error, what we're seeing here is we're running each of when I run mod sample, it's running each of the chains in serial. So there are 4 chains by default. It's telling me that there's a exception that happened. So this is sort of like a prefix for the chain 4. If you look up here, you'll see that this should have repeated for chain 3. and same for chain 2 and chain 1. The error here is that there's an exception. Normal LPDF on line 11 is failing. So here, line 11. What are we seeing here? Random variable 1 is NaN, but must not be NaN. So the random variable, this is given by Stan. So normal LPDF is actually this function call here. We're using normal here, but this is syntactic sugar, and it's really what's happening under the hood looks more like this. All right. So that's what's happening under the hood. This is closer to what happens under the hood. So this is the function that's being called. It's the first position is, we call that the random variable. This is the mean, and that's the standard deviation. That's what will happen if we change what else is NaN. You see this 1 here, it's saying that the first element of Y is NaN. It must not be NaN. So first thing we can do, we'll add, how many of you are familiar with print statements in Stan? You use this a lot? Okay, cool. So if you're familiar with print statements, that's great. We're going to do that. You need to recompile this model, and then you can run it again. All right, so run it again. We get a lot of output. So what we're going to do here, I'm going to run it with 1 chain, 1 sampling iteration, and 1 warm-up iteration. I'm not really interested in finding out what's happening other than trapping this error. I put in this print statement. Anyone have a guess as to why I don't see it here until I get all the way up? So that's where it's being printed. Any guesses as to why this is being printed here, and then we see a bunch of other things? Yep. Well, first, Y is being printed as NaN, NaN, NaN. So we haven't set Y to anything, so it's just being initialized with NaN, not a number. What's happening here is that Stan is going to take this and it's going to try to initialize a model, and it's going to pick a random starting point for mu and a random starting point for sigma. It's going to try evaluating that. And it's running into an exception. Normal LPDF random variable is NaN. And it's going to reject that first initial value. It's going to reject the second initial value. It's going to reject the third initial value. And it's going to keep going until, should say, it should reject 100 times. That's what it should do. So that's what's happening right now. The model can't start. So let's start by replacing the vector Y with this code here. Any questions so far? No questions. Okay. Let's talk about blocks real quick. So this is in the transform data block. The data in the transform data block run exactly once per execution, per time you run the Stan program. The parameters block gets it tells the Stan program what it needs to define as parameters, and then the model block runs multiple times per iteration. So this is run exactly once, and this is run for every iteration, but it could run actually a lot of times. If we have a generated quantities block, This is run once per iteration. This is one. Program. This is run per per um per iteration. Okay. So let's replace this with that. Save it. If I run this again, all right. There are two errors, well, one error and one warning message. Anyone have an idea of how to read this warning message here? Or this error? This is a compilation error. All right, well, all right, I'll just walk through this. So there's a difference in standard between compilation errors and runtime errors. We won't work too much on compilation errors. Presumably if you start writing stand, you'll get comfortable with these. But I will show you how to read this little block here. Yep, there's a type mismatch. So the left-hand side has type vector and the right-hand side has type row vector. It's trying to tell you exactly what's wrong. So here, vector y, and we're trying to assign it a row vector. To make that an actual vector, we add, as Trin says, you add an apostrophe and that does a transpose. And that'll get us past this error here. The warning here is that this is a warning from read lines that it doesn't like incomplete final lines. So if we're gonna go back here, added the line, and that warning should go away. That's a R issue, not really, it's not really an issue for anything else. All right, if I run this, okay. Now when I run it, I see the chain for chain one. I'm running it with one chain, one iteration, one warm up. I've got my data looking like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's how I assigned it. It still rejects the initial value a few times, and then eventually it finishes. All right, so what is it doing? What's it rejecting? Scale parameter is minus, it's a negative number. The scale parameter is sigma here. So sigma must be positive, and it's going to reject that. It's going to reject this one because it randomly drew a negative number, and so on. But at some point it does complete, and then it does that. Any questions so far? If not, we can go and actually run this model. Okay. So with parallel chains equals 4, I'm running each of the chains in parallel. This is a very fast model. I can do fit. You're gonna see mu is close to what I'm expecting. SD is not. I mean, it's kind of close. You might not pick it up, but you know, it's not actually close to what we're expecting. So why is it not the correct model? I think Trin mentioned it earlier. Let's see if everyone else has caught on. Or it might have been Marcus. Okay, Trin suggesting one fix. Let's do that. So by doing this, we're telling Stan that sigma must be greater than 0. right? Uh, if you're not familiar, Stan actually samples. So the parameters that Stan uses are not these parameters. There's a set of unconstrained parameters that sometimes map exactly to the parameters you have, but here it's going to have this, doing this is equivalent to, um, so I happen to know this exact transform. So what's happening is we're going to define a parameter that's on the minus infinity to infinity scale, and sigma itself is the x for that, and that's going to be positive. But we don't have to do this work. We can let Stan do this for us. We do that, and that'll force sigma to be positive. That still doesn't fix the issue though. Right? This model, if you looked at it, you'd expect um, sigma to be close to 1 to 10, like that. Anyone realize what the conceptual error is here? Index, yep, Nicolo, you got it. Um, so one thing we could do is add that. Mu is a single parameter, sigma is a single parameter, right? So the trickiness here is that if you weren't paying attention, you might miss a bug like this. Um, so you kind of have to know what your model, you kind of have to expect what your model should be doing in order for you to pick up on something like that. Yeah. Um, right now it's a little high. That's fine, I think. Is it 1 to 10? So that's going to be times 9 divided by 10. Is that the right one? Or is it the other way? I forget. Anyway, that that happens. We're good. Um, any questions so far? So far we've hit a compilation error. We've printed out NANs. We've looked at error messages. We found an error in our model. All right, here's something we can do, something that if you're not familiar with, you can optimize this model. You see that the print still happens, so why is that? If we do that, we've optimized this model. And we can get the MLE out of this. Yeah. If you notice, we haven't put any priors on here. Is that a problem? Yes, it's a problem. Anyone else have a different opinion? Um, it it, it depends, right? It does use an uninformative prior. You can see that by doing this. Yeah. So if we change our data to n equals 0 and y, we actually don't even need to set it. Um, then what's going to happen if you don't put a prior is that we're ending up with a what you call it, an improper posterior. So this error for us in a different way. Um, if you do this, right, what's fit going to do? Mu seems to run forever. Sigma's pretty large, 10 e to the 300 is not good. You're going to see that a lot of transitions ended in a divergence. It just doesn't know where mu and sigma should be, right? So if you did something like that, you solve this problem. It just goes away. One of them ended in a divergence. If you don't want that divergence to be there, one of the tricks is to increase this adapt delta's default is 0.8. We increase it to 0.9, and it's actually going to force the step size to be smaller. And it should work here. Yep, that's that. Why is sigma double checking? Why is that sigma that? You could do something like R norm, a big number, 0, 1, take the absolute, and then we'll take the mean of that. And that's the number that we get. So it's sampling right. If you wanted to take a look at it, you could also do something like take the histogram of that. Oh, that looks squashed. Okay, that's what that looks like. If we do MCMC hist of sigma, and that's what the posterior distribution looks like of sigma. All right, on to example 2. Anyone else want to? Does anyone have any questions on example 1? It's really simple. There are plenty of other things we can mess with. All right, I'm going to move to example 2. Oh, did I just? Oh, hey, look at that. Example 2 was set up exactly like how we ended example 1, but we're gonna see a different error. All right. First of all, this when we run it with, we'll take a look at this program real quick. Transform data is y equals 0. I put no priors on mu and sigma. With no data, this is ending up with none of the chains finishing. Right, so it's unable to print. We just don't have a successful output. If we do that, we can see the error messages. What's happening is numerical overflow and metric adaptation. It's trying to tell us here, this may happen when the posterior density function is too wide or improper. So we have an improper function, an improper model. And that means that the integral of this model is not a finite number. So here it's, it'll run to infinity, and that's what's happening. Funny enough, I think if we do this, we break it. Let's see. It may not be enough. Yeah, so that actually runs when we constrain sigma to 0, but when both of them are left unconstrained. we run into this issue. The first thing I wanted to show was that this error is actually different than the one we saw before. So while we still have the exceptions happening, what we're ending up with is that it's actually going through the iterations. It actually initialized properly. It wasn't like our first example when we started where we couldn't get past initialization. Here, the initialization happened, but it's having trouble keeping the parameters in a good spot. So it's gonna keep rejecting each of the proposed parameters. See the notes I left to myself. Okay, so why is this different? What can we do to trap this? Any ideas? Have any of you printed out the target before? There's a function inside stand called target, and that'll print out what the target value is. So do this. So what I'm doing here is within the iteration, I want to know what the target is at the start of the loop of the model. I want to print my mu and sigma so I know what values I have and what happens after I run this code. Stand is a what you call it? No. Stand executes each of the lines in order, so it's not going to go and rearrange the lines for you. So it'll just run everything and you could print and it'll print what's happening there. Let's do this. One chain. All right, I'm gonna stop this because we don't actually need to see what's going on. Does anyone see the problem? What's happening here? So what I'm saying here is that before before I start anything, my target value is 0, which is fine. My mu is this value, my sigma is that value, and the chain at the end, the target value at the end is 0. So there's no information that's getting to my posterior distribution. It's the model is flat everywhere, right? So nothing I do in this block matters. Um, I could evaluate if I run this again, I could evaluate like the number 0, the number 1,000, and it'll still be 0. Um, what ends up happening is if we do something like this, you're gonna see this target change. So before target is 0, at the end it's going to be minus 0.05. And this, with these values of mu and sigma, it's a different value, right? So that's good. That's what that is. Any questions? Anything? All right. If we go back to the original example, we'll see that it throws divergences, right? And let's talk quickly about what a divergence is. So if you go back to example 2, if you set it back to what it was, I'm pretty sure I put it together slide. So what exactly is a divergence? Is there an easy way to print to a file or other output? Good question, Robert. No, not through command stand R. Uh, I mean, you can sync it. We can't do it inside stand. I think we can. I'm sure I could hack something together, but there's no option to do it right now. What we could do is use command stand itself to do it, but there's no easy way to do it. Good question. All right, so what's the divergence? So Hamiltonian Monte Carlo simulates trajectories. So the there's a potential energy and there's kinetic energy. The potential energy is the negative log probability density at a particular point for the parameter values. So if the parameter values are in a good spot, it has high potential energy. If it's in a bad spot, it has low potential energy. Um, the way HMC works is that you inject kinetic energy from that spot, and energy should be conserved. So high potential energy plus kinetic energy should equal a constant. How Hamiltonian Monte Carlo and the no U-turn sampler simulates trajectories is it does numerical integration. It takes small steps. So it tries to adapt a step size, so it estimates a step size to take, and then it takes steps in that direction according to the gradient and using the kinetic energy and the potential energy. The divergence occurs when this integration fails to follow the true trajectory. How do you know that it's not following the true trajectory? At every time that you take a step, you could just compare the energy. When you start, you knew the potential energy of where you started. That's the initial conditions of that particular chain. And then you knew the kinetic energy that you're adding. And you know that this is supposed to be constant. So if you take a step forward and follow the kinetic energy, and it should stay really close to that constant. And if you take 10 steps and that constant is not close to the constant anymore, then you know it's off. Um, it turns out when you do this type of simulating of trajectories, once you start going off, uh, it'll go very far off of this constant value. Why is this happening? It happens when the posterior geometry is tricky and that gradients differ in magnitude wildly. We're talking about orders of magnitude with different parameter values. And that's when it ends up not being able to follow the trajectory, and then you see it flagged as a divergence. Um, so by doing this, we can force a divergence. Right? If hopefully you do this again and again, you'll see that it just ends up in divergence. We've warmed up with one iteration, so it hasn't had a good chance of estimating a good step size. And then we're just going to try to sample one chain. So it found a valid place to start the chain. And then so mu starts at 3 and sigma starts at 2, so it's valid, right? It'll it'll be able to do well, there's no data, so it'll work. Um, but it's going to try to follow this trajectory and it's just not working. So that's what's happening. It's been about an hour. Does anyone want to take a break for a couple minutes? All right, welcome back for anyone here. Thanks for hanging out with me today. Um, let's see. How's it going so far? Do you want me to move a little faster through these examples, or are you trying to type as we go through? All right, we're back. We'll start working on non-identifiability. Um, let's start with this slide here. I threw this slide together last night. It's, non-identifiability is tough. I think it's the most common problem. Um, and it's really not, is the parameter identifiable in a statistical sense? Like, is there enough power to tell whether or not I can estimate this parameter? It's really like in the simple case, it's two parameters that you can add together to be a parameter that you can estimate, but the two parameters together, you can't. It can be multiplicative, it's label switching. When you get more complex, you get into nonlinear functions. I've seen it in ODEs with parameter scales. I put in quotes harmonics because, like in music, you got a frequency and you could have it double and quadruple and whatever, and you end up with the same um, inferences happening. And that also happens with STAM programs and models. So we're going to see an example of a non-identifiability here. Let's pull up example 3. Um, it's pretty simple. Data is, the number n. You have a vector y. So here it's inside data. We're going to pass data in. We have three parameters, a and b, and then a third parameter sigma. And the model is going to be the data y is normal a plus b, right? If we had this as a single parameter, it should work fine. But because we have two parameters and we don't give it any information, it's going to fail. So here we go. Feel free to set your own seeds, whatever, make it bigger. Something I want to show is here's how you can write out this data to file. So if you ever wanted to read back from the file, so n is that, y is this. If you want to read back from the file, it's that. So you don't lose it. Those are the same values here as inside this data file. Compiling the model. All right, I ran it. Josh, you have a question? Well, whenever you're back on, just go ahead and shout the question. So if you see this type of error, it says variable does not exist, processing stage, data, initialization, and then variable name is n. So it's telling you that I didn't pass in data, right? That's what this means. It's looking for base type is int. So if I do this, we should expect missing input data for the following variables y. Okay, so we need both. So if you ever see something like this, that's what's happening. All right. So what's going on? If we look you see a bunch of transitions in divergence. Well, not that many in divergence, but a lot of them hit the max tree depth. If you look at fit, A is looking like it's minus 285 at the mean, posterior mean. B is the negative of that number. We can actually take a look at this here. Right. And if you look at B here, it should be the opposite. And if you do compare them together, you kind of see what's going on. So this is an example of an additive non-identifiability. Like I said, when things go wrong, it feels like a vibe. Right, A and B could be estimated this way, and it's fine. But why is it not right? When I look at it, I know that my data is really like minus, it's on the order of 1, right? Minus 1 to 1. There's no reason for the mean to be any of these any of these mean parameters to be estimated at 200. Um, anyone have any ideas of how to make this work? Remove A or B would be the easiest, sure. Um, that's definitely yeah. So real mean. Is that gonna work? No, real mu. All right, so this is definitely going to work, right? We should get a mean of um, whatever mean of y. It should be close to that for my example. Okay, so that's what I got. Um, we can add. Let's do what Stosh says. Let's try that. We can add a informative prior. By the way, we're just gonna go and work through different things that we can do to make this better. Hopefully you'll see something new. You might not. That's cool. You might try something that you wouldn't have thought of before. Stash, what's a informative prior here? Very informative. All right, let's do that. Okay. Do we need to add both? I actually don't know. Let's check it out. Well, by the way, that's good. I would be more oh yeah, sorry. This is yeah. Please send it to everyone. This is all right. So, oh no. Yep. Robert's exactly right. This actually comes up a lot in real models. Um, whether or not it's the right model is a different question. Sometimes you want it. Um, sometimes it doesn't. You don't. We're just going to do that so that we can see it at the end. So interestingly enough, if the data has a range of one, I would think that the prior on the mean, so on mu, um, might actually be, the way I think about it is I would do something like, I know mu isn't here, but zero, SD of y divided by square root. And then sometimes I do stuff like that just to make it even tighter. So maybe I would do something like this. And then it's actually not by the square root of n, it's half the variance. So you square this, divide by times 0.5, and then take the square root. Every so often I end up doing stuff like this too. Because I know this a parameter is actually supposed to be the mean. And I know that the standard error of the mean is going to be pretty tight. All right, here a is now 0.2, b minus 0.2, b is like that, and we said the mean of y is that. So lo and behold, we are now in business. Okay. Um, another trick that I use sometimes is this here. Um, so if you have a and you have a b, I could force b to be bigger than a by setting this. Right, so I'm putting a lower bound. Yeah, sure. Um, so the SD is that. Yeah, work. Just nope. Sorry. Um, prior on A equals the SD posterior on A. Do you mind explaining that? I'm missing it right now. Oh, I see. You're saying that the prior on A. Got it. So what Stasha's saying, I think, is that you're comparing the prior to the posterior to make sure that there's some learning that's happening. And you could definitely do that. So that would be something like, yeah, that's a cool trick. So we'll go back. It draws, let's see, a, so that's the standard deviation of that. But if we do our norm and just simulate our way through this, 0, 1, but we're bounding it by 0. So if we take the absolute value, it'll do it. Take the SD. A is a little bigger. Let's see what happens to B. Is that sort of what you're thinking about? So posterior is a little wider, I guess. That's all right. Doesn't matter so much. Okay. All right. The other trick I was going to show was we can do this as a lower bounded variable. Oh, nice. Yeah, I see. So that's going to force A and B to be um, that's going to force B to be greater than A. Let's see. Um, how do I do a trace plot? Uh, Forgot how to do a trace plot and uh, phase plot. Let's see, trace. What I thought I was looking for. Oh, so B is greater than A. Um, guess what I could do is that should do it. Yeah, B is always going to be greater than A. If you wanted the other way around, you could do upper bounds work 2. This doing these tricks actually changes the model, so just beware. And it's ending in a divergence right now. I didn't put enough. Um, check the rank. What does that mean? Check the rank. This one, a rank hist. Actually, don't know what that does. So let's do it together. Okay. So yeah, so we've gotten into a non-identifiability just with two parameters for mean. Easy enough to figure your way around this. Mu here is it's always gonna be right about the right place. Um, but A and B are, there are different ways to model this and get yourself out of this. Um, how do you identify whether or not you have this sort of problem? Sometimes you're going to end up with slow sampling. Sometimes you're going to see, you know, if you do plot plot the scatter, you're going to see a pattern. Sometimes you'll see a pattern that looks like that. Yes, all the material is available online. You can go here. Um, you're welcome. So you can see patterns like this in your posterior, and you're gonna think about it and say that shouldn't happen that way. Um, yeah, Robert, it's a cool trick. There's actually a more natural way. I should have brought this up earlier. It's ordered to let's do um see, I guess. So C1 is normal 0, 1. And then just so that we're on the same page, real A equals C1, real B equals C2. And that's what it's going to look like. A is non-scope because A is non-scope. Could do that. Some C, I could also do C1 plus C2. Right. And we're going to get back to fitting things the way it was going before. All right. This fourth example, I was gonna try to use, I was gonna try to compile methods, but I was actually having trouble with this yesterday. So let's see if we can do it. Compile model methods. If not, we'll have to skip a bit of it, but we'll still work on speed stuff. So when you do compile model methods equals true, this will enable command stan R to run the log prob and grad log prob. So the log prob is going to be this block here. You pass in parameters and it's going to understand it's going to understand how to put it in, and you're going to be able to evaluate the target. Grad log prob will not only evaluate the target, but it will also evaluate the gradients of that particular location. Um, Again, I was having trouble last night running this, so we'll see if we get any further today. While we're doing that, let's look at what BFMI, low BFMI is. Okay, so that one. So it's if you go into this, the conceptual introduction to Hamiltonian Monte Carlo, it'll explain. So Trin, I'm going back to your question, asking about low BFMI. Um, the answer is gonna be here. Type answer there. All right. I'm still compiling. If you're all still compiling, that's what's happening. In the meantime, let's see. Once again, you can write data out to a file and can save it. If you're not familiar with profiling, if you ever want to get into speed, let's see. Yeah. All right, let's talk about improving runtime speed. If you're ever talking about improving runtime speed, please don't try to mix code optimization and model changes together. I mean, you can. I often do, and then I kick myself for doing it. Um, they're two different things, and you want to know whether or not your changes in optimization, code optimization in the stand programming actually affects the model or not. You want to measure what you can. So before going and altering stand programs, oftentimes which are hundreds of lines long and kind of work, you want to know where the bottlenecks are. So we'll talk about profiling. One way to do that is to create reproducible examples. The way I usually work is I serialize data out and then use that data again and again to make sure I know that my improvement in wall time is happening. Um, and there's something to know that there's a difference between the speed of computing the log prob and the gradients themselves. So that's how fast you can compute the function. Um, if you program better, you'll compute the same thing faster, hopefully with not that much difference in numeric computation. Um, but there is a difference between that. That's only going to get you um, percentages of speed. But if you actually change your model so that the no U-turn sampler is good at providing high effective samples, that's going to give you orders of magnitude. So there is a difference between that. Um, and I think naively people think that the number of parameters is the problem, but it's usually not. You can have a lot of parameters, and sometimes adding more parameters will make the speed better. All right. So this is what I ended up with again and again last night. So I don't think I'm going to be able to figure out what is causing this today live. But if this were to work properly, you will be able to do something like first you do this, then you're able to do run the log prob function, and then you could put in a small one. But that's not, it'll fail again right now. So I'm not going to do that. Okay. So if we do something like this, we can profile this and we're going to add, um, yeah, there might be something wrong with the make file. Um, no profile sound. Let's see what happened. Example 4. Okay. So I'm just making it so that things print out all the way across. Okay. And we'll walk through what's happening here. There's data n, vector y, parameters mu sigma. We're just doing a simple normal model, nothing complicated. We're going to profile this, and we're going to call that the likelihood. When you run this, it actually writes to a file, and it'll have this profiling information in it. Command-CNR lets you pull that out and just use this profiles function to look at it. So this is the block that I defined. I called it likelihood, so that's that. Thread ID, we don't have to worry about that. This is the total time that it took. So it's not, this model is very fast, so nothing. There are two different times, forward time and reverse time. The forward time is the time it takes to compute this value. So the target, so it'll be target plus equals normal LPDF mu sigma, y mu sigma. That's taking this much time. The reverse time is for it to do auto diff, right? And this is the size of the different auto diff stacks and the number of calls. So chain one called the auto diff stack, sorry, it called it 11,542. Each of the chains called the auto diff calls a different number of times. That'll have to do with the number of warm-up iterations and the sampling. Yeah, that's that. Let's see. So if I were to make this faster, right, what I would normally do is I would start here. I would copy this. Do that. I'd first run this version to make sure it is doing the right thing. Right, so hopefully this and this look very similar. Everyone following along so far? I've just copied example 4 to different executable, a different stand program, and running it again. You'll notice that the calls have different, autodiff calls have different stack sizes, but the forward time, the total time is about the same. If we wanted to, what we should do is do something like this. So when I typically do something like this, and I'm working purely on speed. So right now, let's talk about how we get this to go faster. I would do chains equals 1, seed equals 2025 1103. So that's today. Let's put so the original ones here. So fit. So if I run fit profiles, and I run all right, so the first thing that you should know is that if you set a seed, the data is the same, the output should be identical. There's no So if I took draws of mu, I'm taking any one, right? And I do an exact equal, this should be the same. I know you're not supposed to compare floating point numbers, but here we're running the same program. Bitwise, it's going to repeat exactly the same process. So that's not going to change. All right. So now what can we do to make this, to understand what's going on? Right now we've got nothing in this program, so it's really easy. So I know that we can vectorize this. If we do this, it should be faster. So now how much faster are we going? It's about twice as fast. You should see that the number of turns out that there's a little bit of difference in the way it's run. We set the same seed, right? So this is where it gets tricky. We have the same seed, but now the output's different. The reason I know that the output's different is I'm looking at the number of out-of-diff calls. They're different. So that means that the numeric computation is slightly different between the two. And that's going to be down to rounding error at this point. Um, if I wanted to really pin that down, I can do this. Okay. So fit draws. Let's just take a look at mu. Oh, it did completely starts in a different spot. So there's not really a way for us to actually. All right, there we go. Okay. Oh, okay. So there are 2,000 iterations. So we'll look at the first iteration. So what I'm trying to show here is that um I've got my original program and it's looping through this log probability distribution function. So this is equivalent to target plus equals normal LPDF yn given mu sigma. There's single mu, there's single sigma. There's not much that's going to change other than this y. I know the code, the C++ that computes this, and it should use the same mu and sigma, but since the code is vectorized, it actually computes it slightly differently and has a different order of operations, and that's going to add a little bit of rounding error. So as it's going through the Hamiltonian Monte Carlo and it's running through it, you're going to see that the original and the faster version are staying together until um, iteration 55 of warm-up. And when I say that, we can look at iteration 55. Let's see. I can do it. No, that doesn't do it. Let's see. All right, they look the same, but they're not, right? So yeah, let's do that. I don't know if this is actually going to work, but we'll see. No, it's not going to do anything for us. Okay, that's fine. If someone actually knows how to make all the digits come out, let me know. Oh, print headed digits. All right, there we go. Thank you. All right. So now we're at some point in here, the numbers like that, whatever decimal point that is. It's really small. So what ends up happening here is you're gonna find that at iteration 55 was the first place it drifts, iteration 67, 69. And then it gets to a point where the errors add up, and let's see, 121, and then starting at 122, it goes off. 21. And then at 122, these things should start drifting. 3. And once it gets there, it's no longer going to be the same change. All right. So why am I talking about this? Once you get to things not being the same, it's really hard to compare when you're looking at the total output time, the total wall time, right? The total wall time now is uh, if you look at the profiles here, the number of auto diff stack calls are different. So that's going to make a difference there. All right. Yeah. Okay. Are y'all still with me? We'll try this one other example, and we'll call it quits after that. There's an example 5 in here that is, we're gonna do a sum of exponentials. It's gonna be a log normal model. It'll be a little, we're gonna simulate data. We'll see what happens. So I'm gonna simulate data, set my A to minus 0.3, B to minus 2. So when I run that, what I'm ending up with is a bunch of speed up warnings and divergences, right? So what can we do to make this better? We can add priors like we did. We can add lower bound sigma, because that shouldn't be negative. Just add a non-informative prior. I mean, I don't know. If this was real life, I'm not exactly sure what A and B should really be. Hopefully it's driven by something I know about the process that's making this data. I made up this data. I don't know why I picked these numbers, other than I thought it'd be an okay example. Uh, Let go of exact profiling, but trust my gut. So the conclusion of the previous example is use profiling to tell, but separate out once you're no longer running the same code, like you're no longer getting the same exact output. You actually have to trust the profiling to help you understand what's happening. Because the wall time is going to change, you're going to get different effective sample sizes, but the time it takes to compute a single log prob evaluation should be real. You will notice bigger changes anyway. Yeah, absolutely. If you get orders of magnitude difference, that's great. That that in the last example, I know the model hasn't changed, so there's no reason for the algorithm to pick up that one model is actually significantly different than the other. Um, it'll depend on random seeds. So one other thing you can do is cycle through a bunch of seeds and cycle through a bunch of data to make sure that the effects that you're seeing are real. Um, and with this, let's see. So fit, I'm not, oh, sorry about that. I'm not estimating these parameters correctly. So what I actually want to do with this example was start here, and then if we look at X and Y, sorry about that. Give me a second. Um, oh, I thought I had more plots here, but I didn't. Okay. So if I plot these two, X and Y, you see a little you see that it's not really easy to distinguish. So some tricks I have for simulating data start with something simpler. So I drop sigma down to 0.01. I can increase n to like 1,000. So I'm making sure I know what's happening here. Um, so that's what my curve looks like now with these two curves. I fit this model. Um, right, the same program. I didn't change anything about the program. I just changed the data. Um, I just changed the data. Then what you end up seeing is that the model starts fitting better. With that said, I'm still getting this weird A and B happening to be, oh, A and B are swapping um values, right? So summary. So A I have as minus 0.3, B is minus 2. And I think this is the one where I can go and say or equals A. So if I do something like that, I want A to be lower than B, because what's ending up happening is that this is like a non-identifiability that's happening here. We can run this, and that should help with this particular problem. Okay, so X, Y, and sigma's that. Oh, good question. Let's see. The answer is probably yes. Here we're not, if we go back to not doing this. So the mode's happening in two different chains, right? So this is an interesting, just a thought experiment here. Since we're in Bayesian inference, uh, if we think that the let's see, okay. Okay. Yes, exactly. If ESS is about one, what's our hat? It's actually driven by our hat. Our hat is 1.73. R hat should be close to one. That means that the within chain variance and the between chain variance are similar. Um, okay. If you to think about Bayesian inference and you knew that A and B could, there's nothing in this model as written that says A or B should be, one of these or the other, right? So if we were to trust Bayesian inference and get the right estimate out, then A should actually be jumping between both modes, um, both both these values. Um, right now we're getting chains that are going between them. If we waited long enough, and if the MCMC algorithm was correct, uh, then we would actually see a single chain going back and forth. So, some of the problem is that if we only run a single chain, we're going to miss that sort of problem. Um, yeah, but since A and B can looking at this model, right, there's nothing that says A should be close to 5 and B should be close to 0 point or minus something. Then we're not going to get, there's just, uh, A and B should be both of those values. The distribution of A should incorporate both of those values. Let's see. Um, yeah, anyway, I think what I ended up doing here was if you do that, you set a better prior on these, even if it's too tight, it should end up working out. Oh, I didn't put a prior on sigma. Log normals have really fat tails, so they're really wide at the large values. So if you end up giving it just something reasonable here, it might be the trick. Um, all right, here the numbers are positive, but if you look, let's see, generated quantities. I'm pretty sure this is going to work out just fine. Okay, that's the last of my examples. Just a quick wrap up and Q&A. I'll show what happens to this after we're done. Some key takeaways. First thing, understand the error message. Understand what you're trying to debug. If you don't understand that there's a error, then you won't know to go find it. The way to really debug is simplify the program, try to trap it, reparameterize, write the model slightly different, run it again, validate that the problem has gone away. And the last thing is debugging is really, in this sense, model building. It's not like software where the input and output, if you change the code that happens in between, but you get the right output, that's just the way it's supposed to go. In model, if you change the stuff inside, it's often a different model. And I don't know, I've come to embrace it. So that's about it. Thanks for hanging with me. Please reach out if you have any other questions. That's my email address. That's just reach out on LinkedIn. Happy to connect. I can stay for a few more minutes if anyone else has any questions. Hey, Harvey.
Hey, I just wanted to jump in and say thank you so much, Daniel, for such a fantastic workshop and all of your insights. It's truly great when we get an expert on who can give us all of these amazing insights. So I really appreciate your time and everyone's contribution to a really nice discussion as well.
Yeah, thanks everyone for hanging out for 2 hours. I know it's dull. It's a it's a technical thing, but I don't know. You don't often get to see people live code and make mistakes. So
it's not dull, especially for this audience. Maybe for others, but for this audience, it's captivating. So thank you so much. We really appreciate it. Victoria and I put in the chat if you want a completion badge for this, please just put in the form. Really appreciate everything. And just to let people know, there's another 3 workshops today, or another 2 workshops today happening this afternoon in the US, Europe time, and then more conference kicks off later this evening, our time, but morning, Asia Pacific. Okay, well, thank you so much once again, Daniel. Really appreciate this. Really appreciate your time. And I'm going to close the bridge. Daniel's put his contact details in there for anyone who wants to follow up. Close the bridge now.